Thank you. Is it bouncing? La la la. The audio, it go la 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 la. All right, great. I will begin with a word of prayer then. Heavenly Father, we thank you for this day. Thank you for these students. We just pray you bless this class today, Lord. In your name I pray. Amen. All right, so I will get started. My apologies to those of you who were forced to come late because apparently we don't know when classes start here. Not your fault, but anyway, the show must go on. So I want to talk about linear independence. Of eigenvectors. All right, so it's just a little leftover. Hopefully, shortly after I get done with this discussion, it will naturally lead us to the next thing, which is the Jordan form. Now, I will tell you this. I'm really thinking about the field being the reals or the rationals or the complexes today. For the most part, actually, I'm thinking about the field being the reals. And some of what I'm saying, actually what I'm about to say equally well applies to a finite field. So, but anyway, here's the theorem. If, let's see, if we have V1 and V2 and V3 eigenvectors for, let's say, A in n by n matrices over F, all right, with eigenvalues lambda 1, lambda 2, lambda 3 respective, and lambda 1, lambda 2, lambda 3 are distinct. All right, if those are distinct eigenvalues, then this triple V1, V2, V3 is linearly independent. Right. Now, I thought about it. I could start with proving it for 2, and then I could give you the proof for k by induction or something, right? But I thought about it. I thought, you know what I should do? I should show them the proof for 3. If you really understand the proof for 3, the general result or the result for 2 is easily seen. So I think if we can work it out for 3, we should be good. And so that's what I'm going to do. So here's the proof. We'll assume that C1V1 plus C2V2 plus C3V3 equals to 0, where A Vj is equal to lambda j Vj for j equals to 1, 2, 3, right? And what else? And Vj is not equal to 0 for, you know. So I probably should have put the last part of that sentence as a standalone sentence before that, right? So, you know, when I'm writing proofs on the board in here, sometimes I get my thoughts out of order, and that's on the. Anyway, we're assuming eigenvectors 1, 2, 3 with the distinct eigenvalues lambda 1, lambda 2, lambda 3. I want to show that forces linear independence of this triple. Okay. Now, so what I'm going to do is I'm going to multiply. Let me give this thing a name. Let me call it star. I'm going to multiply star by a particular thing. By A minus lambda 1 times the identity matrix, right? And I'm also going to multiply it by, multiply by the product of this and this. Okay? Hey, question. The matrices I just wrote down and I'm about to underline in green, do those commute with each other? Does this matrix and this matrix, do these commute? Is it true that this is equal to a minus lambda 2I times a minus lambda 1I. Is that true? Well, a certainly commutes with itself, right? And you may recall this dark moment in your academic history where you were asked to calculate the center of the set of all matrices, the set of matrices which commute with all the matrices. And what did we find what that was? We found it was multiples of the identity matrix, right? So we know that lambda I commutes with anything. So in short, yes, that is true, all right? What that means then is when I multiply star by that product, I can either think of the one with the 1 coming first or the one with the second coming first. It's, you know, it's just the same. So if you look at that, what I got, and I'm going to just go ahead and, you know, skip a step or two here, but I'm going to pull the C1 out, and I've got as a minus lambda 2I times a minus lambda 1I on V1 plus C2 a minus lambda 1I a minus lambda 2I on V2, right, plus C3 and then a minus lambda 1I times a minus lambda 2I acting on V3. Right? Now that's all equal to 0, right? So why would I do such a thing? I do such a thing because, see, V1 is in the null space of a minus lambda 1I, right? So V1 is in the null space of a minus lambda 1I. And well, in fact, that's Vj is there, right? I mean, that's true for j equals to 1, 2, 3. Right? That's equivalent to what I just wrote down here, right? We can either think about an eigenvector as being a vector that when we multiply the matrix on the vector, we get back a scalar multiple of the vector, namely that eigenvalue. Or we can think about it as being a vector in the null space. Okay, guys, so what's this? That's 0, right? What's this? That's 0, right? And then what are we left with? How does this calculate? This right here. Let's do the calculation. So we've got C3 a minus lambda 1I, and then we've got a v3, right, minus lambda 2 v3 equal to 0. But what is a v3? A v3 is lambda 3 v3, right? So I can pull that v3 out. In fact, I can rewrite this. I can rewrite this as c3 times lambda 3 minus lambda 2, and then I've got a minus lambda 1 I hitting the vector v3. What happens when we multiply v3 by that matrix? So by almost the same calculation, we get that C3, lambda 3 minus lambda 2, times lambda 3 minus lambda 1, V3, is 0. So what's this tell us? What do we say about the eigenvalues? They are distinct. What's that mean? That means that their differences are not 0. Right? So we have C3 times a non-zero number times another non-zero number times a vector, V3, which is by assumption what? Non-zero. This implies then that C3 is equal to 0. 1 down, 2 to go. Right? So continuing, we've got C1 V1 plus C2 V2 equal to 0. So multiply by a minus lambda 1I, or, well, Yeah, a minus lambda 1I, the above. What's that give us? What's the question? No question. Something exciting happened this weekend? Kind of party or something? No alcohol, of course. It's liberty. I understand. Right? Okay. Just checking. Drugs are bad. Don't do drugs. So here, I was raised in the 80s. It's part of my upbringing. You know, just watching cartoons, minding my own business, and there's some lady cracking eggs in a frying pan and saying it's your brain on drugs, and so it's you know, it's something to think about. Anyway, my parents' generation, for whatever reason, was dodging missiles from the Russians, so it's kind of an improvement. You know? What's the next? I guess the current generation has other problems, but anyway. So by construction, this is 0, right? And what's this give us? This gives us C2 times lambda 2 minus lambda 1 V2 equal to 0 by the calculation I just gone through. But again, the difference of lambda 2 and lambda 1 is non-zero. The vector V2 is a non-zero vector. When we have a number times a vector being 0, we proved at the start of all this that we have a cancellation. If you have a scalar times a vector is 0 and the vector is non-zero, it means that the scalar must be 0. So the scalar here being 0 forces C2 to be 0 because the difference of the eigenvalues is non-zero. Right? Hence, star reads C1 V1 equal to 0, which of course then implies C1 equal to 0. So we have shown that setting the linear combination of eigenvectors with the distinct eigenvalues to 0 through a straightforward series of calculations implies that all the coefficients are 0. So consequently what? Thus, V1, V2, V3 is linearly independent as advertised. In fact, I mean, you can already see in my proof how you do it for 2, right? Stupid, but I thought I'd do it for 3 because the third order case really includes the idea of multiplying by the product of everything except for the one you're after. And this generalizes. There's a theorem. If we have, you know, V1, V2, Vk, subset of, well, V actually, and you have T of Vj equal to lambda j Vj for distinct distinct V1, V2, Vk, all not equal to 0, then the set containing those vectors is linearly independent. So once you have this theorem, which the proof of is in my notes, all right? And there's really two ways. I've showed you the constructive proof today. But there's also a proof of these things by contradiction that you can read in my notes, okay? Which is the proof most people show. The proof by contradiction goes something like, suppose there's a linear combination, suppose there's a linear combination such that one of these coefficients is non-zero. Then that means you can solve for one of the vectors in terms of the linear combination of the remaining ones. And then that gives you a contradiction because that actually then implies that the coefficients are not distinct, well, they're assumed to be distinct. It's something like that. But, I don't like to do a contradiction proof when I have a perfectly good constructive proof like this. And I also like this proof because it illustrates some of the central calculational ideas of eigenvectors, so I think it's a better proof, and that's why I showed it to you. But if you think about it, once you have this, right, if you suppose you have eigenspaces, you've got, E1, the null space of A minus lambda 1I, and you got E2, the null space of A minus lambda 2I, and so forth, right? suppose you got it all the way out to, I don't know, suppose there's S of them. Right? Where I'm assuming that lambda 1, lambda 2, lambda s distinct, okay? Think about what happens if you have a basis beta 1 for this one, if you have a basis beta 2 for this one, right? If you have a basis beta 3 for this one, 3, maybe S. Okay. I think that the theorem that I've just proved for the case 3, you can kind of see how maybe you can start to see if we use beta is beta 1 union beta 2 union beta s, right? And the number in beta 1 plus the number of things in beta 2 plus the number of things in beta s, if that's equal to n, which is the dimension, well, if it's equal to n, where I'm assuming a is n by n, do you see how you'd be able to prove that the union of those is a basis? I mean, first of all, if the number of them is n, then all we have to do is what? To prove it's a basis for Fn. It's got the right number of things, right? Fn is n-dimensional. So to prove that that's a basis, we just have to show that that's a linearly independent set. Yep.
The last beta in that
That's an S, yeah. Sorry. So if you think about it, though, almost the same calculation we've just gone through will prove linear independence of this basis, right? So if you have something like a sum over C1 I1 of VI1, V1 I1, and then you got the sum over C2 I2 V2 I2, sum over, I'm sorry, I didn't want to get into this much detail. It's too late though. SIS, VSIS, something like this. And so what I'm saying is each one of these sums is taken over the basis. So like this one has V1, 1, all the way out through, I can't even fit it in here, I'm sorry guys. Let me just say it in words rather than writing more letters. So what I'm envisioning here is a linear combination where I'm writing the first linear combination coming from the first basis, the second from the second basis, all the way out to the S1 from the S basis, right? So to kill off everything in this sum except for the last sum, what would you do? How would you annihilate all of these? You just multiply by the product of a minus lambda 1i, a minus lambda 2i, all the way on out to a minus lambda sub s minus 1i. So by multiplying by the product of a minus the eigenvalue for everything except for the last one, you can kill off all the sums up to this point, at which point you have that this sum is equal to 0. Then by the linear independence of the this basis, you get that those coefficients are 0. And then you just multiply by the product of everything except for the, up to the next to last one. And then that will prove that the next to last coefficients are all 0. And you just continue this process until eventually you just have that left, which you can show as 0 again. So what I'm trying to say is if you can prove it for just a vector from each one, you can generalize the proof to a linear combination of vectors one at a time. If we were all more conversant in the equivalent characterization of the internal direct sum theorem we had, that we can write V as an internal direct sum, there's 5 different conditions, right? Independent subspaces, unique representation of the element, unique representation of 0, that you can concatenate bases to get a basis for the whole space. And then what was that fifth one? I can't remember what the fifth one was. Oh, the definition, that it's isomorphic to the direct product of the subspaces, that there exists that isomorphism, right? Really, if we were completely immersed in the proof of that, then you'd realize I'm just recreating that proof right now. So, but anyway, long story short, if we have sets of eigenvectors, right? If I have a set of eigenvectors, which all have eigenvalue 3, all right? And that set of eigenvectors with eigenvalue 3 is linearly independent. If I take that set and I adjoin to it another eigenvector with a different eigenvalue, it maintains linear independence. So linear independence of pairs of eigenvectors with distinct eigenvalues automatically linearly independent. So given this, can you guys tell me, if I have a 3 by 3 matrix, what condition can you give me that would force diagonalizability of the matrix? Suppose we have A is, I'll keep it real, a 3 by 3 real matrix with lambda 1, lambda 2, lambda 3, then a diagonalizable. What condition do I need on these to make that happen? Distinct, right. So if we have an n by n matrix with n distinct eigenvalues, it's diagonalizable. So really, the fussy question with regard to diagonalizability is when we have a repeated eigenvalue. Right? If there's a repeated eigenvalue, then we're not sure whether or not we have enough eigenvectors to form an eigenbasis. And as we learned last time, that is what we need for diagonalizability. Let's see here. Words. Yes?
Can you have a linearly independent set of vectors if the eigenvalues are not distinct?
Yeah. The example that worked out at the end of the last help session, which I pointed up to the board in here in the last class, there we have a repeated eigenvalue of 4, and there's 2 linearly independent eigenvectors. But it doesn't have to be the case. For example, if you had this matrix, 3, 3, 3, 1, zeros everywhere else, you can easily check that AE1 is 3E1, and you can check that AE3 is 3E3, right? But if you look at it, AE2 is, what is it? Oh, I'm sorry, I can't do math. I make that 2. Sorry. You can easily see that AE3 misbehaves, because there we get 0, 1, 3, right? Which, by the way, is E2 plus 3 E3. Now, I guess that doesn't prove. I mean, I'm asserting that there are only 2 linearly independent eigenvectors with eigenvalue 3 here. What's the characteristic polynomial of this one? So the wonderful thing about determinants is it does blocks, right? So we can look at this block and that block. So we get 3 minus lambda. The determinant of this block is, well, I mean, there's something, let me say it in a different way. This is a triangular matrix, right? So we could just multiply the diagonals to calculate the determinant. And so we have lambda 1 equals to 3 thrice. Sorry. Anyway, the algebraic multiplicity here is 3. The eigenvalue is also 3. Sorry, it's hard to see the contrast of 3 on 3, but there it is. But, you know, biblical integration, I suppose. Now, so what's A minus 3i, though? That matrix is 0, 0, 0, 0, 0, 1, 0, 0, 0. What's the basis for the null? What's the basis for the null space of this matrix? Right. See, because the basis for the null space is the eigenbasis for the eigenspace with eigenvalue 3. It's the span of what? What is this? What's the null space of this? What does it force on us? If we have an element of this, suppose that u comma v comma w is in the null space, all right? If u v w is in this null space, what can you say about u v w? What's that? U is 0? What about v? I mean, what's this matrix say about the null space? I think it just says that when I multiply this vector times that matrix, the only condition I get, in fact, is just w equal to 0. That's it. There is, in fact, no condition whatsoever on u and v. U and v are free. All right? So the one thing you can't do is to make them both 0, because then you'd be just left with a 0 vector, which is not an eigenvector. So anyway, long story short, we have a basis 1, 0, 0 and 0, 1, 0. So my point is, when you actually go through the calculation, my claim is correct. There are 2 eigenvectors. There are 2 linearly independent eigenvectors, and at most 2 linearly independent eigenvectors with eigenvalue 3 for this matrix. All right? So this matrix is not diagonalizable. We proved last time, if and only if there's an eigenbasis, is the matrix diagonalizable, right? I've shown you that the eigenvalue is 3 repeated, and I've shown you that this is, by the way, this shows that the geometric multiplicity is 2. This right here is the algebraic multiplicity of lambda 1 equals to 3 is 3. We have a theorem that says the geometric multiplicity is at most the algebraic multiplicity. When they're equal for each eigenvalue, that's when we get diagonalizability. Okay? But that's a good question. You know, is it possible to have, you know, not as many vectors as the algebraic multiplicity? Yes, it is possible. That's exactly what we're confronting today. That's why we need this thing called the Jordan form. The Jordan form picks up where diagonalizability leaves off. The Jordan form is it's a pattern. It's a shape we can transform the matrix into using a similarity transformation, right? In fact, in the same way that we transform a matrix into, how do we transform a matrix into diagonalizable form? What do we do? Guys, you remember what's the algorithm for diagonalizing a matrix? Step number 1, find all your eigenvalues. Find all your eigenvectors, right? If possible, we do what? We construct eigenbasis, right? Call that beta. And then if we look at beta inverse, A beta, we proved last time that that gives us a diagonal matrix with the eigenvalues down the diagonal. Right? That was the procedure, basically. 1, construct the eigenbasis. 2, similarity transform. That gives you the diagonalized form of the matrix. Right? Conversely, or correspondingly, if we have a linear transformation and we want to find a basis where the formula for the linear transformation is absolutely most beautiful, most simple, we choose the eigenbasis. Right? So what's the analog of this for the Jordan form? Let me just tell you. So in the Jordan form case, very similar story. Number 1, we construct generalized eigenbasis made of chains. And step number 2, guess what? beta inverse A beta will equal to the Jordan form. All right. So what I'm going to start with here is I'm going to describe for you how we construct the what does a generalized eigenbasis mean? What's that look like? I'm telling you this Jordan form is a generalization of the diagonalizable form for a matrix. So you shouldn't be surprised when I tell you to start with that an eigenbasis is an example of a generalized eigenbasis. That's the sort of most basic example. But here's the definition. If we have A minus lambda I to the p power acting on v equals to 0, but A minus lambda I to the p minus 1 acting on v is not equal to 0, for v not equal to 0, then v is a generalized eigenvector of order p. So let me show you an example of this symbolically, okay? Suppose you had something like A minus lambda I squared acting on v equal to 0, yet A minus lambda I on v is not equal to 0. Then that would make v a generalized eigenvector of order 2. My quote-unquote p is equal to 2. Here's the neat thing, guys. What happens, so let me call this thing, I'm going to call this thing v2, all right? Call that v2. Call that v2. I'm going to let v1 equal to A minus lambda I acting on v2. Let define, okay? Can you guys, well, what happens when we take A minus lambda I acting on v1? What happens then? A minus lambda I acting on v1 is what? A minus lambda I acting on v2 squared, right? Which is what? That's what? That's, you're right, v1 is an eigenvector, but you're fine. This is 0, right? Which proves what you said, which is that v1 is an eigenvector. Wait a minute. So you mean to tell me that if I have a generalized eigenvector order 2, I automatically get an eigenvector from that? Yes, indeed. Pretty neat. So this thing here, v1, v2, is a 2-chain for lambda with respect to A. Let's see here. Suppose we're dealing with like a 2x2 matrix. All right. So for the sake of discussion, if A is 2x2, consider L sub A, right? That would be a mapping from F2 to F2. Let's find out what's the matrix of L sub A with respect to this two-chain basis. Let's call this thing beta, and let's find out what happens. By the way, you can prove it's linearly independent. Linear independence comes from calculations much like I've shown you today. You can prove it. If you take a linear combination of C1 V1 plus C2 V2, if you act by A minus lambda I, it kills off the V1 piece, leaves you C2 times the non-zero vector 0. That gives you C2 0, then follows C. Anyway, linear independence follows from calculations much like I've done already today. I'll leave it as an exercise for you guys. I mean, I kind of told you just now, but. All right, so what is the matrix? What's the matrix of L sub A with respect to this beta basis? How do we do that? We're supposed to do A times V1, the beta coordinates of that, right? And then A times V2, the beta coordinates of that. So what's that look like? Well, AV1 was equal to what? Lambda V1, right? We just proved it's an eigenvector. So we got lambda V1. And what's AV2 equal to? The answer is up here, right? So if you look at this equation right here, you can see that AV2 is equal to V1, right, plus lambda V2. See that? So AV2 is V1 plus lambda V2. So you guys tell me, in the beta basis, where beta is V1, V2, what is the coordinate vector of lambda V1? I'll do this one. You guys do the next one. It's lambda 0. Tell me what this one is. What's that? 1 lambda. We have a winner. Very good. This, by definition, folks, is the 2 by 2 Jordan block for eigenvalue lambda. So I invent a notation for this because it's special to us. It's dear to us. This is J2 of lambda. Okay. The 2 by 2 Jordan block with eigenvalue lambda. Now, if you can do it for 2, you can do it for 3, right? So if I had a generalized eigenvector, what if I had A minus lambda I on, V3 equal to 0? Oh, sorry, that's squared equals to, good grief. V3 like this equal to 0, but A minus lambda I squared V3 not equal to 0, right? Suppose you had a generalized eigenvector of order 3. Then you could say, aha, well, I'm going to make A minus lambda I acting on V3 equal to V2. And you could make then A minus lambda I acting on V2 equal to V1. All right? And if you do this, in other words, we start at the top of the chain, V3, and we act by A minus lambda I to go down the chain. And if you work it out, you'll be able to prove. So this right here is just me. This is me giving a definition for V1 and V2 on the basis of V3. Yeah. No, just one copy. And that's one of the beauties. Part of the beauty of this calculational method is that, in fact, we don't actually have to power the A minus lambda I up. It suffices to look at A minus lambda I in parts of these calculations. I mean, I actually will not completely describe to you guys how to find the Jordan basis, nor will I require you to be able to find it in general. Usually if I ask you to calculate the Jordan basis for a matrix, it's a pretty simple matrix. So some of the subtleties which appear in the general case won't appear for you guys. backtrack. So anyway, so here you can prove a minus lambda I squared on V2 is equal to 0, right? And then you can also prove that a minus lambda I on V1 is equal to 0. So to get the first thing I wrote, you just take the definition for V2 and multiply by the square, right? We just take this, right? Just multiply star by a minus lambda I squared, right? So then you get a minus lambda I cubed on the left-hand side, and you get a minus lambda I squared V2 is 0. And if we call this star star, multiply by, well, I guess I could take, how to say this? Yeah, this one, multiply by just a minus lambda I, right, on star. And use star star star, which would be this. Anyway, the point is, if you start with a eigenvector, a generalized eigenvector of order 3, you produce a 3-chain, right? You get beta equal to V1, V2, V3. And if I look at L sub A, if I suppose A is 3 by 3, and I look at L sub A being a map from F3 to F3, you know, suppose A is 3 by 3 for the sake of our discussion here, then the matrix of L sub A with respect to this 3-chain basis, what it's going to look like is lambdas down the diagonal, right? So basically V1 is an eigenvector, right? But how does V2 work? What is the deal with V2? A V2 is what? It's lambda V2 plus V1, isn't it? And what's A V3? It's lambda V3 plus V2. So the fact that A V2 is lambda V2 plus V1 puts a 1 on the superdiagonal here, and a 0 down here. And the fact that, you know, this puts a 1 on the superdiagonal for the third column, like that. This, folks, is what's called the Jordan block of order 3. This is the 3 by 3 Jordan block with eigenvalue lambda. Okay? So in fact, to answer your question earlier, was it Ben? What did I do? What was this? This thing here was actually J1 of 3 direct sum with J2 of 3. What I did was I took a direct sum of Jordan blocks. By the way, a single number on the diagonal is a 1 by 1 block. So J1 of lambda is just as stupid. It's a 1 by 1 with a lambda. Yeah. So that is a good start. So I've kind of described to you, so what is a generalized eigenbasis? So definition, generalized eigenbasis is basis formed by linearly independent generalized eigen chains for A or T. Again, T being a endomorphism from V to V, V being a finite dimensional vector space, or A being an n by n square matrix over the field. Now here's the theorem I won't prove. Theorem: there exists a generalized eigenbasis for A in Fn by n whenever the characteristic polynomial of x has all its roots in the field. So like that's not always the case. The rotation matrix we looked at last time, it had imaginary roots. So it didn't have real eigenvalues despite the fact it was a real matrix, right? So the Jordan form is a little bit special in the sense that we need to have eigenvalues, right? We need all of the eigenvalues to lie in the field. But if it is the case, then there's another theorem which says that if we take that generalized eigenbasis, we take this generalized eigenbasis and we similarity transform A like that, or if we look at the matrix of T with respect to beta basis like that, then with respect to the generalized eigenbasis, the matrix looks like the following. It looks like something like, ji1 of lambda 1 direct sum ji2 of lambda 2 direct sum direct sum jis of lambda s, where I1 plus I2 plus IS sums up to n, and the lambda 1, lambda 2, lambda s need not be distinct. But anyway, if you have all your eigenvalues, you can always find a generalized eigenbasis which puts the matrix into this very special form called the Jordan form. And this guy's is more generically, this is by definition the Jordan form. So like my example was the Jordan form, all right? A diagonal matrix is a Jordan form. See this, guys? This one? This is nothing more than J1 lambda 1 direct sum J2 lambda 2 direct sum direct sum J1 lambda n. Did I say 2? I meant 1. These are all stupid 1 by 1. The diagonal matrix is when all your Jordan blocks are 1 by 1. Right? Let me give you another couple of examples, and we'll stop for today. So, let's see here. So guys, can you tell me what that one would be? So how about this one? This is what? This is J2 of 1, direct sum with what? Right, J2 of 0. How about this one? J2 of 4, right? What are the eigenvectors here? I can tell you eigenvectors for this matrix are E1 with lambda 1 equal to 1, and E3 with lambda 2 equal to 0. And there is also a generalized eigenvector of order 2, both for 1 and for 0, namely E2 and E4. For this one, I can tell you that we have E1 and E3 are eigenvectors with eigenvalue lambda equals to 3. And I can tell you that E4 is an eigenvector with eigenvalue 4. And I can also tell you that there are, in fact, 2 generalized eigenvectors in the standard basis, namely E2 and E5, are both generalized eigenvectors. I can tell you that just from looking at this and really thinking through the examples I did today for you. You can string them together. I mean, I did it for a 2 by 2 and a 3 by 3, but you can put these ideas together for larger matrices. What's the basis, for example, the basis for lambda equals to 3 in this case is the span of E1, E3. There's something called the generalized eigenspace. I use a K for that in the notes. Like K lambda 3 is the span of E1, E2, E3. All right? So this is the generalized eigenspace with lambda equals to 3. So we also talk about that. So the generalized eigenspace for a given eigenvalue, it will contain in it all of the chains with that particular value in the basis for the generalized eigenspace. So to find the Jordan form, you have to kind of take those chains apart and separate them and untangle them to find the specific blocks. That's what's really complicated calculationally that I won't insist on you guys learning. Yeah. Oh. Have a good weekend. By the way, something came up. I won't be able to be here Monday, so I'll post a video for you guys sometime. You watch it at your leisure. I'll see you next Wednesday. So.